Hello and welcome to the new workshop on heat transfer in pipe and Nusselt number calculation and comparison with the analytical model that is given by Ditius-Boulter correlation for turbulent pipe flows or turbulent internal flows. So, first of all, if I describe the problem, this is the turbulent flow, and based on the Reynolds number, the Reynolds number definition is that it is the density times velocity times diameter if this is a pipe, and if for the flat plate this would be the length divided by viscosity. So based on Reynolds number for internal flow, the flow becomes turbulent when Reynolds number is greater than 4000. Okay. So for this problem, Reynolds number, we are starting from the 10,000. Then also we will get a solution for 20,000 and 60,000 and 1 lakh. Okay. So for these all cases, basically the idea is that there are two heat transfer modes. One is three heat transfer modes, but mostly we are interested in the two heat transfer modes. The one is the conduction, and the second one is the convection. So if I write down here the laws for conduction, it is the Fourier's law of conduction, that is the Q is equal to minus K. This minus sign is that the direction of the heat transfer, to make it correct. So minus K A delta T by delta X. And area is the normal surface area perpendicular to the direction of the heat transfer. And the convection is given by the Newton's law of cooling, and this is Q is equal to H A delta T. So obviously the H will be having units of watts per meter square Kelvin, and the K will have the units of watts per meter Kelvin. So there is a one length unit is missing in the K. Okay, so the conduction in the conduction problems, the K is the thermal conductivity of the material, and that is a known property. And area we can find out very easily, and delta T we can determine, and delta is also known for that particular thickness of the geometry. So the problem here is to find out heat transfer rate. But in the case of convection, the mostly the problem is that to find out the heat transfer coefficient. This is very important because if there is a combination of the conduction and convection, we can find out the value of heat transfer rate from the conduction, because in the steady state heat transfer rate should be equal. And we know the weighted area, and also we know the delta T. This is also a question that how to find out this delta T, which is also topic of this whole exercise. So the most important thing is to find out the heat transfer, convection heat transfer coefficient. And from convection heat transfer coefficient, we can find out the Nusselt number, that is equal to H times diameter divided by the conductivity of the fluid. This is not a conductivity of the some solid bodies, but this is the thermal conductivity of that particular fluid that is being is flowing over there. Okay. So to solve this question, basically when we apply heat transfer in some region, we can apply heat transfer by two methods. Either we can provide the constant temperature, or we can apply the constant heat flux. In both cases, we can get the solutions. We can have we have the analytical correlations. Okay. So what I did here is that I made a one pipe, and I assumed the diameter, or I kept diameter of pipe as a 1 meter to make the calculations simpler. Okay, then from the correlations for the turbulent pipe flow or turbulent internal flows, the L by D ratio is given by this correlation. So if I put the Reynolds number value, for example, 10,000, the entrance length is equal to, because diameter is 1, so entrance length is 4.4, and for 1000K, for 100K, the entrance length is 6.8. So what is the entrance length? Basically, when flow starts to enter some bodies. So initially the flow is uniform at some location. Okay, and as it moves along the pipe length, what happens that because of no slip condition on the pipe walls, the flow will start to stick there, and as also when the one element or the one particle sticks there, it will also affect the second particle and then third particle and then so on. So what will happen is that this uniform flow will be affected by the presence of the wall, and eventually this will form as some profile, and that's known as the velocity profile. And up to certain length, this will be in the transition, means this will be developing into some profile. But after certain length, what will happen is that this profile will remain same and this will not change. That's known as when the flow becomes fully developed. So for laminar flow, this length is little bit longer, and for tubular flow, this length is little bit smaller. So the condition is that after this condition, what will happen is that the velocity will no longer change in x direction. Okay, but definitely there is a change of velocity along the y direction. That is because of the for that thing we get the boundary layer. Okay, so it means that when the velocity is not changing from one location, let's say we are getting profile here, and this is the point we want to see values. So exactly on the second location of the x, the same location in the y, the value of velocity will remain same. That's why the change in the velocity is same along the x direction. Okay, so but to be on safe side, what I did here is that I provided the entrance length as 20 meters, and this would be the unheated region, because once the flow is fully developed, then if you apply the heat transfer, we can only get the effects of the heat transfer. Otherwise, if you apply it from the beginning, we will get the mixed effects of the flow development and as well as the heat transfer. That's why we have to provide some region that is unheated region where the flow will be developed, and we get the velocity profile like this. For turbulent flow, for laminar flow, this will be a parabolic. Okay, so after that, I provided the constant heat flux, and those are the 50 watts per meter square. Okay, now what does it mean? It means that if the pipe length is 10 meter and pipe diameter is 1 meter, so circumference would be the pi d, that is 3.14, and the length is 10. So this is 31.4 meter square is the surface area of the pipe. So if you apply this one on this thing, it means that we are applying basically 50 into 31.4 watts. So, but if you make it per unit area, this is equal to 50 watts per meter square. So for the 1 meter square area, basically we are applying the 50 watts. Okay. So this is the starting of the problem, that we are starting with the problem. And so we have the Reynolds number, and we got the diameter of the pipe, that is the 1 meter. And then from the entrance length, we found out the unheated region, and I doubled it, or almost more than double, and made it 20 meters, and then provided the 10 more meters for the where the heat transfer or the thermal boundary layer will be start to develop. And that's why I will also get the values of the thermal conditions or the heat transfer coefficients almost at the end of the pipe, that is the close to the outlet. Okay. So this is the problem definition, and from the heat transfer coefficient, we can find out Nusselt number. This is what we are going to do in this whole workshop. Okay, and then compare with the correlation. Okay, so this is the all the given conditions. We have the inlet, we have the outlet, we have the two walls, unheated wall and the heated wall. Heated wall has a heat flux of 50 watts per meter square. And the viscosity and density are taken for the air, and then we can find out the values of the velocity from Reynolds number, viscosity, diameter, density. So we can use the Reynolds number formula, and we can find out the velocity, which is equal to Reynolds number times viscosity divided by density divided by the diameter. So it becomes 0.145. So this is about this whole problem description.